Moving on with our discussion of ways of introducing the carbonyl function, the aldehyde or ketone, into a molecule. Method 4 is Friedel Crafts acylation of aromatic compounds. We'll illustrate this with benzene. I'm going to draw the two hydrogens in that are around the reactive site. The reagents are an acyl chloride, I'll simply use acetyl chloride. This is a simple acyl chloride with Lewis acid, often aluminum chloride, but it could be ferric chloride, FeCl3, or tin tetrachloride. SnCl4 or FeCl3, a Lewis acid chloride, basically. And this is going to activate the carbonyl group. It's not catalytic. You need a full equivalent of the acetyl chloride, or of the aluminum chloride, because we'll see that the aluminum chloride actually ends up bound to the carbonyl oxygen in the product. The solvent for this is often some polarly coated solvent like acetonitrile or nitromethane. Something that will dissolve the organic materials as well as the Lewis acid, which is a salt. And these are just salts. Product will be acetophenone, after an aqueous workup, which is usually not shown in the reaction. So the question is, what's the mechanism? How does this work? We know that the aromatic group is nucleophilic. It has that pi system that could be able to attack an electrophile, but we also know that there's significant stability associated with the aromatic ring where those pi bonds are interacting with one another. So it can't attack just an ordinary electrophile like bromine, for example. It needs a much more powerful electrophile. So the purpose of the aluminum chloride here is to convert the acetyl chloride, which is electrophilic, into a much more potent electrophile. And what will happen is the chlorine from the acetyl chloride will act as the Lewis base to attack the unfilled octet on the aluminum chloride. Making aluminum tetravalent, and thus possessing a formal negative charge, and the origin chlorine having a positive formal charge. A pair of electrons from the oxygen can now come in and push this chlorine out. Chlorine doesn't really want that positive formal charge. And we will generate the residence stabilized acylium ion and tetrachloroaluminate, which is fairly stable. Negative formal charge of the aluminum. Fairly stable tetrahedral say aluminate 3 because aluminum can only do a 3+. Right? So that's a tetrahedral tetrachloroaluminate complex ion. And we have the acylium ion, which, as drawn here, has a positive formal charge on the oxygen, but there's a resonance structure that has the positive charge on the carbon and an unfilled octet. This is by far the major resonance contributor. Being the one that has the filled octet on both carbon and oxygen. But again, great rule of organic chemistry number 1 says that if you want to understand reactivity, you can often understand it best by looking at the minor resonance structure. If the minor resonance structure has a positive charge and an unfilled octet on carbon, that's pretty unstable. Benzene is going to be able to attack that. This is a much more powerful electrophile now than the starting acetyl chloride, which had a partial positive charge on carbon. But everybody had filled octets, it was relatively happy. So good nucleophiles will attack acetyl chloride. An amine would attack acetyl chloride, for example, to make an amide, and we'll see that later in chapter 19. But if you want a core nucleophile like the aromatic ring to attack acetyl chloride, you've got to activate it and convert it into the acylium ion. Once you have the electrophile, the acylium ion, electrophilic aromatic substitution is a relatively simple reaction. It's just 2 steps. It's the electrophile being attacked by pi bond, and that breaks the aromaticity of the ring temporarily. And you'll notice that to avoid having 5 bonds to carbon, I had to push a pair of electrons onto the oxygen at the same time. So we no longer have an aromatic ring because we've broken that 1 pi bond. To regenerate the aromatic ring, we want to take this hydrogen off and convert this back to an sp2 hybridized carbon. The tetrachloroaluminate ion will do that by donating one of its chlorines. And it's very important that you always take off the hydrogen adjacent to the positive charge, which was true for E1 elimination last semester as well, and never the hydrogen that's on the carbon bearing positive charge, which would generate a carbene, and is relatively uncommon. So that will generate HCl gas as a product. And it will give us our ketone and aluminum chloride. And because the lone pair on the carbonyl oxygen is nucleophilic, that aluminum chloride will end up complexed to the product until we do the aqueous work. And that's why you need a full equivalent of the aluminum chloride. Up, they'll keep this off and generate aluminum hydroxide and also neutralize the HCl that's produced. So this part is the electrophilic aromatic substitution. Step 1, attack of the aromatic ring on the electrophile. And step 2, regeneration of aromaticity by removal of the proton from the sp3 hybridized carbon. So that's electrophilic aromatic substitution, which occurs after we generate the electrophile in this 2-step process, where we have nucleophilic attack on the unfilled octet on aluminum, followed by tetrachloroaluminate falling off to generate the acylium ion. And I just write down that this is called the acylium ion. So this isn't limited to acetyl chloride. Any R group here will result in a different R group there. So we can make a series of ketones of various length by simply choosing the right acetyl chloride. So a good way to make ketones, but it doesn't work for converting benzene into benzaldehyde because the corresponding 4-amyl chloride, the 1-carbon analog of acetyl chloride, is unstable. So does that mean that we can't make benzaldehyde by electrophilic aromatic substitution? No. We can, in fact, make benzaldehyde by electrophilic aromatic substitution, but we can't do it from the unstable 4-amyl chloride. But we can, in fact, generate 4-amyl chloride in situ, or generate it in place, by mixing together carbon monoxide and HCl. In the presence of both aluminum chloride, which is the standard catalyst for Friedel Crafts reaction, and cuprous chloride, copper-1 chloride. These copper-1 halides are useful reagents that we'll see again later in a reaction called the Sandmeyer reaction when we get into the aromatic compounds. So we've got the aluminum chloride. The aluminum chloride is going to react with HCl to generate a really acidic species. It's capable of protonated carbon monoxide. And we will once again generate the tetrachloroaluminate ion. So that's an even better acid than HCl, which was already a strong acid. And the purpose of the cuprous chloride is to complex with the carbon monoxide. The triple bond likes to bind to copper-1. We saw that in the Soto-Ishiro reaction where a cuprous ion was used to insert into an alkyne CH bond. So we'll form a complex between the carbon monoxide at the copper-1, where the pi bond is bound to the copper. And that will allow the carbon to get protonated by this kind of super acid to generate the 4-amyl chloride, or to generate the 4-amyl ion, right? The equivalent of a psyllium ion, still bound to the copper. So we get this HCO plus, which can be used to attack the bond, and we also get the tetrachloroaluminate ion, which is going to serve as our source of chlorine. This now acts just like a psyllium ion. It can be attacked by the pi bond of the benzene ring, which you compare the electron back to oxygen, and the copper will fall back off in the process. And we generate a sp2 hybridized carbocation and sp3 hybridized carbon in the aromatic ring, means the broken aromaticity. So step 1 of the electrophilic aromatic substitution is electrophilic attack by the benzene ring, and then the tetrachloroaluminate ion will once again yodate its chloride and regenerate HCl. And benzaldehyde as the product. And if you've been keeping track fact, there's also a chloride ion floating around that came with the cuprous chloride. This reaction is important enough that it actually has a separate name. It's called the Gatterman Koch reaction. And it's specifically for making aromatic aldehydes from aromatic rings through formulation. Basically, this is a formulation. So Friedel Crafts acylation from an acyl chloride, or the Gatterman Koch reaction generating that kind of acyl chloride in situ from HCl carbon monoxide in the presence of cuprous chloride. So that's new. That reaction is covered in detail. The Gatterman Koch and the Friedel Crafts reaction are covered in detail in chapter 15, and we'll see them again when we get there. So I'm going to stop this video and make one last video on preparation of aldehydes and ketones, and talk about the unique properties of benzoic and allylic positions, where we can use selective oxidation agents.